and welcome. In this video series we're gonna look at capacitive currents and look at systems or components which influences the electric propagation of waves or dielectric fields in order for a load to pick up this energy. The power I'm going to use here, you see here on the left hand side, you see this board which is currently energized. You see in a little screen which I will put here in the middle, which with the second camera you see then in real time the influence I have here on that coil. So that means on the table there is nothing but only this excited field here, and the power is very low. We are consuming currently around 2.5 watt. And I can only, when I initiate that a little bit, I can do it like that, but it dissipates literally here. There's no energy left anymore. The systems I did build here on the table are much more favorable. One you have seen already in before, and I have now built a new one which I will introduce to you in a second. In my comment sections that I have some problems to replicate this one. That is actually correct. However, I did build a new one which is actually much better than this one, and it has only, you see the two LEDs connected here in the middle, has the same length of wire on one side, but it has, as it is here, so by the way this capacitor has no other function just to be connected at the end. However, here I use the small one, as you can see here, and it works very, very strong and also over greater distance. So we're going to look at this one then and compare it to this one. Not that it's really required, but from a performance point of view, but what is important for me is here that I have a device built which is much more, put it that way, sensitive in a way to pick up dielectric energy and convert it into electromagnetic energy in order for this LEDs here to illuminate. I use various capacitors here. I use for testing here, this is two capacitors connected in series. You see here the plates. I use this for the Hubbard coil, and they are there's a metal shield on it and they are gold plated. I have 4 of them, and the acrylic in between is 0.5 centimeter, so it's half a centimeter thick. In between I have the metal, and then we have here the connection, so we have the both outside connected and they are connected here in series together. So we're gonna connect to this here in a distance away from my energizer. Then I have another one which here, so this is my capacitor you've seen before, and again I'm going to use here my vortex field compensators. That means they are actually quite strong in a way. They are tapping into the dielectric field within the dielectric inside here, and we're going to look at that. Of course we have a standard metal plate. A standard metal plate is converting a dielectric field into electric waves. We know that. We know about that. And then we have here an interesting combination. I have here built a capacitor, if you want, 2 half forms, and in between I have a piece of mica. So we're going to use this one, have it like that, staying here at the very end. It's good a meter, it's more than a meter in distance on that coil, and see what influence this has on both of our loads. So from our third test, we're gonna test in general now both of my loads. So we're gonna look at the screen, which will be here in between, which is coming from the second camera. We're gonna see the influence it has. So if you see my hand now moving over here, you see it influences the signal. So what we want to avoid that the signal is going to get influenced. That means we are harnessing energy which is outside of the influential field, which should be here. So if I move my hand here, it doesn't change. If I move over here, it starts to change. That means here's my barrier. That means everything I do here on that side doesn't influence my frequency response of the coil. That means here I'm outside of the direct coupling. Having said that, please forget about near field effects here, because it's dielectric. We are talking about dielectric, purely dielectric. There is no magnetic coupling here. That has to be clear. It has nothing to do with electromagnetic wave propagation. It's a purely dielectric capacitive current coupling, nothing else. And that does not require anything from a tuning point of view. However, if I detune the coil, that has of course also an influence on the capacitive current, which can be propagated through space. That means if I influence that, that means I have less on the receiver side available to pick up for my load. So if I start easily with this one here, you see at this position I have light. Bring it a little bit closer. I go out of the range. I should still have some light here. Yes. See if you can see that. Barely. Yes, it still has light. And it gets stronger. The closer I go here to this one, and it will be much stronger over. There's the closer I go. The further I go away here at that side, here my light is off. So for this load here, my demarcation point is here. I get no light output anymore on this load. Now let's try this one. This one is much more sensitive and can pick up still. Here's the load. And of course, if I use my body and connect on the other side, I have much more current available, capacitive current available to energize that. So that means I am over 1 meter now in distance from that coil, and that means here if I go closer here at that level, I can go even almost to the other side and still have light output here. However, it's not that strong anymore. Both of them don't illuminate when they are out of range. That means when they are over here and they're not hold or in connection to a different capacitor, very important, which can harness the energy, they on their own are not capable to energize enough. I would have to go much closer and want to give you this information as well. If I go here with this load so close, still not energized, I have to go, still not, I have to go so close, not even. And then it doesn't work. Here, only if I put it here on top, it's working. Now, if I put this one, it's working here. Not sure if you can see that. So easy. If I can put it up like that. If it stays, yes, let's see. That's working a little bit. Barely. So the influence of, or the radiation field of the sphere is equal in all directions. And the other thing is quite interesting, and I want to demonstrate that. It radiates out. That means I have energy from the side, yes, but, and from top as well. Oh, you can't see that anymore. I'm out of range of scope. So I can go at least 30-40 centimeter on top of the sphere, and I have output. And you can see that here as well. It has output. See if I can put it so that you can see that. It shows some output, yes. If I take my other load, it's much brighter, much better. Of course, if I connect now here to the capacitor with my hand, it's very strong. And I cannot show that to you. I would have to zoom up to demonstrate that I can go at least 50 centimeters up and I can still illuminate that load. So here, of course, it's very, very strong. Now we're going to move over now to the capacitor. So from a capacitor point of view, we have the three variations. I mean, I can do this one. It is not influenced here by that one. Doesn't do anything. If I put my hand here, nothing. If I go here, sorry, it works a bit, but only because I have a little bit of contact, metal contact out here, that it picks it up. But it doesn't pick it up via the dielectric. That means if I contact only the insulation, the dielectric, it doesn't work. If I contact it with a metal to the field, it works. And the same here. Let me demonstrate it here. It does not work. Now, let's take this one. If I connect this one here, it's good. It's very strong. If I connect it here to the, so you can see that. And maybe to the ball now, or here, let's do it as first here. Of course, if I would go in here, it's very strong. Metal, of course, as well. They're working very well. And here it doesn't really matter if I connect to the copper or to the magnet here at the moment, to the magnet, it is fine. From a dielectric point of view, it works without touching, but if I go closer to here, it's getting better. Now, here says only very little left. It's almost nothing. I'm almost 1.5 meters away. But if I connect now, here it's the insulation to it. Hopefully I'm still in the picture. No, I'm not in the picture anymore. You should still see that. Of course, if I connect now here, it's very strong. So they are giving you, from insulation point of view, they're giving you more surface area for the capacitor. And as you can see here, if I only go here on the insulation, see if that's working. they provide now a vibration between my body now. Or let's do it, if I do it this way, it's clear. But if I do it this way, the vibration is through the insulation, through the two half spheres here, through the two half spheres, and the LED, via the insulation is an increased capacitive vibration or capacitive current coming through it, and it allows me to illuminate the light. So this doesn't show you the direction of propagation, but as a starting point. So I wanted to see if there's some kind of propagation possible into a specific direction, and I will have to investigate with various other forms to do that. But that should give you a bit of information in which direction to go. And also very important, note that when I do my experiments here, that has no influence on the wave at all, on the system. That means my boundary line is here. Everything from here on has no effect anymore on the source. That means every energy I take away from here is not reflected back to the load. However, if I would go over to the other side, there would be a direct connection to the load, and the load would drain the energy from the wave, meaning the wave would drop in amplitude. That would be an indicator that more energy is required to deliver the power to the sphere, or to our antenna if you want. And also more current is drawn from the power supply to energize the coil. I thank you for watching this movie, and wait for our updates when I'm looking at directional dielectric fields for energizing remote loads. Thank you.